Okay, so today's video is going to be on a review for modern physics. To start things off, we're going to be chatting about special relativity. What special relativity, the two postulates that are the framework for special relativity is that all laws of physics are the same in every uniformly moving reference frame. Now, that seems odd, but if you can imagine that and so we have the term uniformly, so we're talking about things that are moving at a constant velocity. If you're moving at 75% the speed of light and I'm at rest, the laws of physics in your reference frame are the same as the laws of physics in my reference frame. And that the speed of light in a vacuum is constant. Now, this may not seem like a big deal, but this has really big consequences. It tells us that if you're moving at that 75% the speed of light and I'm watching you move at 75% the speed of light, so I'm at rest and you're moving at a very high velocity, that your perception of space and time is not going to be the same as my perception of space and time. So a consequence of this, okay, a repercussion if you will, is that time and space are not absolute, they're not constant, so are not okay, so that is a odd thought, that how can space and time not be constant? Well, there's things called length contraction and also time dilation that will change. So what we do know is that the ratio of a distance to time stays the same for length, for light. And then in your effort, the faster you go, the slower time moves, and the shorter distance become in the direction you are traveling. And then we know that everything in your reference frame is normal. So this is not perceived in one reference frame. It's got to be compared from one to another. All right, so what we know about photons is that E equals HF. And we see what I did here is labeled the electromagnetic spectrum. And now earlier in the year you came up with an acronym that can give you the order at which the electromagnetic spectrum moves in. So we have R for radio, M for microwave, I for infrared, V for visible, U for ultraviolet, X for X-ray, and G for gamma. So if you have forgotten your acronym, go back and take a look. And knowing this order is really important because on the radio side we have the long wavelengths, which means it's the low frequencies. And on the gamma side we have the short wavelengths, and that is the high frequencies. Likewise, you're probably more familiar with the Roy G. Biv, the red, orange, yellow, green, blue, violet. And likewise, they have a low frequency side, red being the low frequency side, which means that it has a long wavelength. And then the V, the violet, being the high frequency side, meaning that it has the short wavelength. Now, what you also, two numbers that you should know, kind of the range of that is roughly 400 nanometers to 700 nanometers. And once again, that the red is on the higher side for the wavelengths. All right, so just playing around with this equation, we know that E equals HF, but since the speed of light, the wave equation says that it's equal to the frequency times the wavelength, I can rearrange F and solve for F to make it C over lambda. So we can also say that E is equal to HC over lambda. And so this is often useful and not in your AP reference tables. The next thing that we're going to be talking about is the photoelectric effect. So if you have some metal and you shine some light on it, that light has some energy, HF, and if that energy is high enough, what it can do is kick out electrons. And so all metals have a certain work function, the minimum amount of energy required to kick that electron out. And what we can do is, from a conservation of energy standpoint, is we could say the energy of the incoming photon minus that work function, how much energy it takes to kick the electron out, is equal to the kinetic energy, the maximum kinetic energy of that electron. And if I rearrange this to get K max is equal to HF minus phi, and I look at a plot of kinetic energy as a function of frequency, I see that y is equal to mx plus b. That I have my kinetic energy on my y-axis, I have my frequency on my x-axis, and my y-intercept is negative, meaning that it is going to intercept down below the y-axis, or the negative y-axis, and that y-intercept is equal to my work function. Now another point that's important to discuss is what we call F naught, which is the threshold frequency. That is the minimum frequency at which that light can have. Now the photoelectric effect is important historically because it proved that light has particle properties, whereas Young's double slit experiment proved that light has wave properties. And so putting the two and two together led us to the only conclusion that we can draw is that light has both wave and particle nature. So it's got the duality in that. All right, the next thing we are going to talk about is momentum. So we think of typically momentum as P equals mv, but this requires that something has mass. Well, light does not have mass. However, it has momentum. So if we take the E equals hf, the energy, and we divide the whole equation by c, we have E over c is equal to hf over c. And then that's also, since energy is equal to mc squared, we can write mc squared over c. Now, if we do some rearranging here, I see that one of these cancels out one of those. And so we have mc on the right-hand side. But look, that's a mass times a velocity. So that is a momentum. And that I see c is equal to f times lambda. So if I have f over c, divide by c, and then divide by lambda, I have 1 over lambda equals f over c. So right here, that is equal to h over lambda. And that is the general expression that P is equal to h over lambda. Notice that it does not have a mass term in it. And so this gives rise to a photon's momentum. Now, I also included this other part of this here because this is often useful solving this for E or solving it for momentum like it's already solved. But we have E equals PC. So this is the energy related to momentum by a factor of c. The next that we're going to be talking about, and I'm going to go forward one, is the wave function, okay, based off of Schrodinger's equation. So the wave function, if we were looking at psi as a function of position, okay, so as a function of position in meters, and we are looking, let's say we're looking at something that looks like that. Okay, that's our plot of that function as a the psi as a function of position. First of all, at any point that it crosses the x-axis, that tells me that there is 0 probability of a particle being at that area, that location. And then the place with the greatest amplitude, okay, so let's say this is 1 meter, that's the position there, and this is 3 meters, and this is negative 2 meters. Well, what we can say is that the particle is most likely to be at this location right here because it has a greater amplitude. And it's really actually the square of that function, and hence why it doesn't matter whether it's positive or negative. And then likely this would be a tie here since these have the same amplitude based on my rough sketch at negative 2 meters and 3 meters. So that is the probability of finding a particle at that particular location. And then the last thing that we will look at is the Bohr model of the atom. Okay, now the equation that you have in your reference tables is the energy of the photon equals EF minus EI. Okay, the final energy state minus the initial energy state. And this is really just to figure out how much energy is required to move the electron from one state to another in the Bohr model of the atom. And also notice that, you know, if you want to excite an electron, so let's say path 1 versus path 2, okay, so let's call this 1 and let's call this path 2. Well, in order to go up to get excited, you have to take in energy. Well, and then likewise, when it de-excites, it would give off energy. And that energy is equal to h times f. So if I want to figure out how much energy is required to excite it or how much it would give off, because that would be the same amount, is I would take the final state, which in this case, for the simple example, is minus 7 electron volts minus a negative 10 electron volts. So we get a energy difference of 3 eV. Now the interesting thing is that if this atom absorbed 2.9 or 3.1 eV, it wouldn't do anything. And as a matter of fact, that's a misstatement. It wouldn't absorb. That photon would go straight through as if the atom was not even there. But if it absorbs a 3 eV photon, this would get excited to the n equals 2 state based on this diagram. And I could figure out what frequency of light would be required to do so. I could do one of two things. I could either just take the 3 eV, plug it in there, put the value for Planck's constant that's in eV seconds from my reference table, or I can convert the electron volts into joules. That 1 eV is 1.6 e to the minus 19 joules, and then plug that value in and divide by Planck's constant in joule seconds. But either way, I will figure out a frequency of light. Now, if that light is absorbed once again, it would get excited. If it's given off, it would de-excite. Okay, so that's all for today. I hope you found this useful. And as always, I will see you in class. All right, bye-bye.